Hello, everyone. Welcome back to our geometry extension lessons. We are now in our week 6 extension lesson, so our sixth extension lesson here. We're going to be talking about function notation today, so a little bit quicker one. We'll go through what it is, a couple of quick examples, and then get you on your way to your practice problems on Google Classroom there. So we're going to start off with what is function notation. So those of you that may not be familiar with this, function notation is just that. It's a notation that we use to tell us if things are a function or not, and also to help us with some input and output values. So the difference here is we have an equation that says y equals x squared, and we have that same thing written in function notation. So the generic is f. We read this as f of x. So I would say if I were to write that out, it's like f of x. That's kind of how we read it out loud. That letter f can be different letters. You'll see today we'll use different letters, g of x, h. They can be any letter there. The generic one is f for function, but that is the function of x. So the way we read that is f of x. These two things are exactly the same. And as I kind of explain it in the past, I really just say that f of x is really just a fancy way of saying y. So these two things kind of mean the same thing. F of x really means y. It really means your outputs. The only difference here is we can ask for specific inputs of x in some examples, and we'll see what that means. So really, f of x is just a fancy way of saying y. So y equals x squared, f of x equals x squared. They're the same thing. The only difference here is we only use f of x or function notation on things that actually are functions. So for instance, things that pass the vertical line test. So things that are functions like straight lines. So if we had just a couple of examples here, a straight line is a function because it passes that vertical line test, right? If I were to draw a vertical line through any of those spots, it would only touch the graph once. Most of our function families, or all of our function families, I should say, are functions. That's why they're called function families. Things like quadratics, right? And these also pass the vertical line test. Now, it might look in a couple spots like it actually touches more than once, but there's really only one. If I put one x value into here, I'm only going to get one y value back. So if I put 2 into here, the only answer I'm going to get back is 4. That's it. It's a one-to-one function there. So it will one x value will only give me one very specific y value. And that's what function notation represents. It represents these things that are in fact functions. What's an example of not something that's not a function? Just real quickly from a graph, right? I could invert my parabola, so I could reflect it or rotate it, and it would look something like this. And the reason this is not a function is because it fails the vertical line test. It would cross that for one x value, it would have 2 y values, and it would fail the vertical line test. So this is not a function here. That would just be an example of not a function. So that's what function notation represents. You're not going to have to deal with the graph idea of is it a function or not in this lesson. We're just talking about what it actually represents. So what do we have to worry about? How is this used in other ways? So function notation helps us with very specific questions of inputs and outputs. Remember, inputs being your x values, outputs being your y values. For this one, I would have to make like a table of values to see specific x values and what their y values are. And you can do that math in your head pretty easily. But what it really means, what we can do here is we can put a number into our function notation, and now we're asking a very specific question. When it says y equals x squared, that means all the y values for all the x values, right? This is infinite. We can put as many x values as we wanted, and we're going to get the same amount of y values back out. So we can put infinity in here, and then we're going to get infinity back out. For function notation, if I wanted a very specific number, then I would actually plug that in. So a question would look something like this. What is f of 3 equal to x squared? So now notice the difference. What we did is instead of the letter x in the function notation, we changed it to the number 3. And so all that means is that anywhere that you see x over here, you're going to change it to the number 3 and you're going to evaluate it. So if this is something like evaluate, all we're going to do is take the number 3, plug it in for x, and simplify. So what I like to do sometimes is I just put anywhere I see the letter x, I'm going to put a parenthesis, fill in the rest of my stuff, plug in the number 3. I know that 3 squared is equal to 9. And so we evaluate that at 9. Something that might be a little bit different, though, right? That's a kind of a simpler problem because there's only one x and I'm only plugging in one time. If I had another function like g of x, and that was equal to x to the third minus 2x squared plus x, okay? And I said evaluate g of 2. So now what you're going to do is anywhere that you see the letter x, so instead of x, right, we're replacing it with 2 in the function notation. So we're replacing it with 2 in the function notation. So that means that anywhere I see x, like I said, my method, I just put parentheses in anywhere I see the letter x. So I'm not plugging the number in just yet. I'm going to do that just to help me remind myself where I need to plug the numbers in. So I need to plug it in for this x, and for this x here. So I've got 3 parentheses. Notice the cube, the squared, the 2 in front, none of those changed. All I'm doing is changing the x to the number 2. And now I'm going to evaluate this. So 2 to the third power is 8 minus. Order of operations tells me to do exponents before I multiply. So I've got 2 squared. Right, 2 squared is 4. Times 2 is 8. So I get another 8 here. Plus, this is just 2. So I end up getting a 2. How we would write these maybe as final answers here, right? If I plugged in a 3, I got 9. If I plugged in a 2 for g of x, I got 2 back out. So what we would write here is f of 3 is equal to 9. Or g of 2 is equal to 2. What we're saying here, and this is a little bit backwards because of the way that y and f of x are written. This is saying that, remember, f of x is really a fancy way of saying y. So this is saying y equals 9 when x is 3. Remember that this is your x, and this is really your y, or this is your input, and this is your output. In function notation, it looks a little bit backwards there. So this is my input. This is where the x was, right? It's f of x. X was 3. I got an output of 9. So this was x. This is my x, or my input. I input 2 into the function, and so I get my y value, or my output, happens to also be 2 in this case of the problem I made up. Okay, so input here in the function, output is what we get afterwards. Now there's some other things we can do here. So if I take these 2 examples again, so if I actually, let's make up a couple other ones. We'll use some different letters here. So let's say I have p of x equals, let's just go like 2x. And we say that m of x is equal to x squared. We'll take these 2 functions here. We can do some operations with these as well. So you're going to see some practice problems of things like p of x minus m of x. That just means that we're going to take p of x and we're going to subtract m of x. So all we do is we take our whatever p of x is equal to, which is 2x. So I would get 2x minus whatever m of x is equal to, which is x squared. You just write that down, minus x squared. And so that is p of x minus m of x. But you might see this a little bit different. You might see it like p minus m of x which means the exact same thing. So it means I'm taking the p function of x minusing the m function of x. You might also see it like this, where it's p minus m. Now instead of x, I give you a number like -1. All this means is I do the exact same thing. I take the p function, which is 2x. I minus the m function, which is x squared. But now instead of x, I'm going to plug in -1 for both my x values. And you could do that first, or you can do that second, kind of depending. You can just plug it in and then subtract, or you can write the equation and then plug it in. So I get 2 minus, so I plug in -1, -1. Do the math. So 2 times -1 is -2. -1 squared is a +1. So I get -2 minus 1, which is equal to -3. So again, you can plug in -1 first into both of these and then do the subtraction, or you can write out the expression and then plug the number in and simplify. That is up to you. There's one other type, and you'll see plus here, you'll see minus here, you'll see add, you'll see, plus and add, same thing. You'll see multiply, you'll see divide. So you'll see all the 4 main operations here. So it could be p plus m, p divided by m, p times m. You're just going to plug those things in. The other thing you're going to see is something that looks like this, where it's p parenthesis m parenthesis -1. So the difference here is now this is what we call composition. We're not going to get into all of it. It's pretty simple though. Basically, what I'm doing is I'm taking -1 and I'm plugging it into m. Then I'm taking that and I'm plugging it into p. Notice that p of x, the x for the p is normally what's inside of the parentheses. It's now this whole entire thing. So what this means is I'm going to start on the inside. What is m of -1? So we'll start there. M of -1 is -1 squared, right? Because m is x squared. And so that is a +1. So now what I'm going to do is I'm going to take that +1 and plug it into my p function. So now I get p of a +1, which is 2 times 1, which is 2. And so the final answer, p of m of -1, is actually equal to 2. This final one right here. So I started it on the inside. So kind of ignore the outside function. You do m of -1. You get an answer. You plug that answer in and do the p function, and you get your final answer there. Okay. So those are some evaluate, some operations, and some composition. The last thing that we're going to talk about real quickly here is from a graph. So we can still do some evaluations from a graph. So I have a sketch of a graph here. I call this graph g of x. Okay, so this is the g of x function here. It's 1-to-1. It passes the vertical line test, so I know it's a function. And you're going to be asked to evaluate from a graph. So I've got 3 quick examples here. The first one says, what is g of -3? Remember that this is really the x value, right? So this is my x value. If my x values are on my x-axis, this is my input. So what I do from the graph is I go, okay, where is x -3? It's right here. And what I'm doing is I'm looking for the y value that matches with that value. It's a little bit off. I was a little bit off in my drawing, but it's right here, and the y value would be at a +2. So when x is -3, y is +2, and that's our goal. We're trying to find the output. So I gave you an input of -3. What is the output? What is the y value? I gave you an x of -3. What's the y value? If I give you an x of +4, right, an x of +4, so here's the x +4, we look for the y value. What's the y value? It looks like it's about 2.5. And then the opposite of this. What if I said, what is g of x if the output is 0.5? So what is the input if the output is 0.5? So we go to the y value of 0.5, right? That's my output. This is my y value over here. So what's the input? X would be -1 right here. That's the input that would give me that value. And that's how we read it from a graph. That's how we interpret function notation on a graph. So those examples should help you out with your assignment that's posted on Google Classroom. If you have any questions, come visit me during the office hours or send me an email, let me know, and we will go from there. So thank you for tuning in to our week 6 extension video. Hopefully these examples help get you started. And again, if you have any questions, please don't hesitate to reach out. We'll catch you next time on week 7 extension lesson next week.